Alrighty, so I have been getting a lot of requests to explain how I make my helicopters, and so I just wanted to make a quick video explaining the logic and the engineering processes that go into making helicopters like these in Minecraft Create Valkyrien Skies. I'm just going to quickly go over the basic concepts, the basic math and engineering that goes into it, and then you guys, if you want, can take that and apply it to make your own helicopters with your own unique features and designs. So let's get into it. The first, very basic thing we have to recognize is that when air impacts a tilted object at an angle and a high velocity, the force required to redirect that airflow up and over the blade is going to generate a reaction force that pushes the blade down. Likewise, if the blade is inverted, this force is going to be reversed. The magnitude of the force is dependent on the angle, with shallower angles generating weaker forces. In order to build our helicopter's rotor blades, we're going to be using the flaps and the flap bearings from Valkyrien Sky's Clockwork. In order to set up the blades, you simply place the flap bearing down, put flaps in front of it, glue them together with super glue, and right-click the bearing to activate the flaps. You can see that they are no longer blocks. You then apply rotational input to the back, and you can use redstone signals to change the angle at which the flap is set. Additionally, by using computers from the Computercraft mod, as well as the compatibility add-on, you can use the set flap angle command in order to change the angle of the flaps without any input from redstone or rotational force. To do this, you can simply use the .set flap angle command after wrapping the flap bearing as a peripheral. The angle is measured in degrees, and you can set the angle to any angle you want, positive or negative, which will affect the direction, as well as, I believe, decimal values. If you set it to not a number or to too high a value, it will glitch out, you will have issues, so just be careful with your code as to not set it to imaginary values. The simplest way a helicopter can maneuver is by pitching the blades at the same angle. This is known as collective or coal. For the purposes of demonstration, we're going to assume that this helicopter blade rotates counterclockwise, and that when it's marked with green, it is generating upwards force, and when it is marked with red, it is generating downwards force. So for this helicopter rotating, the air is going to be hitting it at this angle, and you can see on both rotor blades, the air is going to be pushing the blade up. This pushes the helicopter upwards. Likewise, if you were to reverse the angles so that the blades were both pitching downwards, it would push the helicopter downwards. Collective is, of course, not the only way a helicopter can maneuver. The main rotor blade is responsible, in fact, for 4 degrees of freedom of motion. This is going up and down, as well as pitching the helicopter forwards and backwards, known as pitch, and rolling the helicopter left and right. The way it achieves this is by altering the blades such that they move in opposite directions. In this case, you can see that the helicopter blade, rotating counterclockwise, is going to be generating upwards force on the right side, however, generating downwards force on the left side. Pushes the right side up, the left side down. This generates a force moment which causes the helicopter to roll to the right. And of course, the way you can use this for a fully functioning helicopter is by applying pitch forces, like so, roll forces, like so, collective forces, like so, and by controlling the yaw with a second tail rotor that in and of itself generates a moment since it's positioned out towards the back of the helicopter, and you can generate force on that simply by adjusting the collective of the tail rotor, like so. It's not enough simply to have those force moments generating at a constant rate. The rotor blade is spinning at a high velocity. So in order for those force moments to be applied in a consistent direction, i.e. tilting the helicopter to the left, we need those blades to be actively updating as it spins. So here's an example. I have a program that's currently, if this were a working helicopter, tilting the helicopter towards our left. You can see the blades pitch down when they're generating a downwards force when they're on the left, and pitch up, generating an upwards force when they're on the right. You'd need to code a system like that generates for collective pitch and roll all at the same time. I like to use just a simple trigonometric formula based on the angle that the blade is at relative to the helicopter in order to determine that. Now, before we continue, you'll need to find the position of the helicopter in the form of several vectors. The way I do this is to just simply use quaternions. Now, that's easier said than done. If you'd like to learn how to use quaternions, I'd highly recommend using the 3 blue 1 brown interactive tutorial. That's how I learned. And it's kind of challenging to get the hang of them, but once you figure out how they work, it's so much simpler than any other method. I will attach code where it's just an additional file that you can add to your program that gives you a function. You put in a 4-dimensional vector and the quaternion, and you get out your nice, simple direction vector. Once you have that direction vector, then you can use that for the following calculations. Now, what you're going to want to do in terms of those direction vectors is to get probably 3 vectors. One vector that goes directly upwards from the helicopter, one facing directly forwards, and then one that goes either left or right. I personally go with left. These vectors will allow you to perform some simple vector calculus and figure out the orientation of your helicopter with respect to the world. You can find these vectors, depending on how your helicopter is set up, either by a single computer that uses quaternions or pitch, roll, yaw, or whatever method you have to find the position of the hull, a computer directly attached to the hull, or what I used for this helicopter, since it was so small I couldn't fit a hull computer, I found the vertical vector by taking the vertical vector from the main rotor blade, because the vertical vector of the main rotor blade is always going to be the same as the main helicopter. Then found the same method, but found the left vector by taking the left vector of the tail rotor blade, since of course that will always be constant, and then finding the front vector by taking the cross product of those 2 vectors. So that's a simple way you can do it without having to use a hull computer if your helicopter is small. Now, the first thing we want to do when determining the orientation of our helicopter is to find the pitch and the roll. These are the deviations of the helicopter from just being perfectly upright. Now, this purple vector represents the vertical vector on our helicopter in relation to the x, y, z coordinates in your world. Obviously in Desmos, z is vertical. In Minecraft, it's y. The way we can do this is by taking the dot product of the purple and green vectors, and as you know, that's equal to the magnitude of the 2 vectors times the cosine of the angle between them, and so you can find the angle between them, and that's going to be your pitch in this case. Now, a problem arises if the vector is not perfectly pitched in either the forward or side direction. You can see with this new purple vector that it is angled slightly between the pitch and the roll direction. If you were to take the angle between that and the upwards vector, you would get some arbitrary angle in this arbitrary direction. Not very useful if your code is oriented around pitch and roll in the x and y directions, or in this case the forward and left directions for your helicopter. The way we can solve this is by finding the projection of this purple vector onto the xz plane. If you think about it, right, once it's on that xz plane, you can find it perfectly with the pitch. Likewise, if you project it onto the yz plane, you'll be able to find the roll. Now, in this case, the x, y, and z are all on the coordinate planes, but in the instance where they're not, you want to find the projection by finding the orthogonal vector to the specific axis, right? If you want to find the projection onto the xz plane, well, you want to then take the vector, the purple vector, or the portion of the purple vector orthogonal to the y vector, the normal vector to that plane. The way you do this is you find the projection of the purple vector, oh, wrong one, onto the y vector, right? This is the component of the purple vector in the direction of the y vector, and then subtract that from the purple vector to get your orthogonal vector. This is the portion of the purple vector not in the y vector's direction. And what you'll see is that this is on that xz plane, and now you can find the pitch simply by taking the cross product. The other mathematical concept you have to know is what's known as a PID controller. This stands for proportional integral derivative controller. Now, say you've got a value like either the angle of the helicopter or the velocity of the helicopter, and you want it to stabilize around a single value. Well, you don't exactly know the forces that are all being applied because valkyrien skies is difficult, so what you're going to use is one of these. Now, this formula looks way too complicated. That's because the people who wrote this made it way too complicated. But what this is 3 different constants, say 10 or 50 or whatever you program them to be, multiplied by the value. So say the helicopter is displaced by 10 degrees, it's pitched too far forward by 10 degrees. This value is going to be 10. And then the second constant the third constant, this is the easier one, times the derivative of the value, so the rate of change. Say it's coming back towards the helicopter at 1 degree per second. This is going to equal -1 plus the integral of the variable. Now, this is the hard one, but effectively what you're going to be doing is as the program is progressing, you're going to be taking a list and just filling it for each value with the current angle in that case, or velocity, or whatever the value is, and you're going to be slowly just adding up all of the displacements. This will make more sense later, but just bear with me for now. So what this does practically is, let's say you have a flying object, that's this little point here, and you want it to be hovering around 6 meters up in the air. This little object represents, say, our drone or our helicopter. In this case, we're stabilizing the altitude with a PID controller. So the proportional section has the first constant times the displacement. Here the displacement is 6, or I suppose -6 meters away. So it's going to be -6 times that constant. It's going to apply, because keep in mind this UT is going to be our reaction that the computer puts in. In this case, it's an upward or downward force. In our helicopter's case, it's going to be angles of the various flaps. This is going to be the roll, the pitch, the yaw that I talked about earlier. So it inputs a force that says go up, and it goes up. Once it gets halfway there, it's now only 3 meters away, and so that constant times the 3 meters is only going to input half the vertical force. And it's going to do that until it gets all the way to 6, right? The problem is, at 6, the force is now 0, but through all this acceleration upwards, it's gained momentum, and so it's going to overshoot 6. And now, because it's at +3, it's going to pull it back down to 6 and slowly oscillate around the value. To get mathematical on this, this is going to be an underdamped system that looks like this. Now, with no other values, this is going to be an undamped system, so it's actually going to oscillate infinitely, which is why you now take into account the derivative section of the PID controller. This, in this instance, is going to be looking at the velocity. So at 3, the force in this upwards direction is going to be halved, And all of this acceleration is going to result in a velocity that's upwards, and that upwards velocity is actually going to be multiplied by a second constant, generating a downwards force. So as it speeds up, it actually pushes it down to resist the speed. It wants to keep it at a low speed, because the lower the speed is, the less it overshoots. And so this is going to eventually dampen it down to 6. That's what either a critically damped, underdamped, or overdamped system, depends on what your value for that derivative is. If it's too much, if the constant on the derivative is too high, you're going to have an overdamped system that starts slowly coming up and then kind of slowly trickles its way up to 6. An underdamped system is going to overshoot and then bounce back and forth until it gets there. What you really want is a critically damped system where it just kind of slides nicely into place. Now, this gets us to our third aspect of a PID controller, which is the integral. This is easier to explain physically. Now let's say suddenly gravity is involved. This ball is being pulled downwards by the force of gravity. So if it goes up to 6, there is going to be no force applied because the speed is 0, so no force applied by the derivative, and the difference in altitude from 6 is 0. It's at 6, there's no displacement, and so that force is also going to be 0. But guess what? There's a force of gravity, and so it's going to pull it downwards. It's going to pull it away because of the force of gravity. Now, there's going to be a point somewhere in there where the force of gravity is equal to the force pushed upwards by the displacement, the proportional aspect of the PID controller. And it's at this point that it's going to hover. Now, the idea of the integral section of a PID controller is that it says every second that this is too low, it's going to add that to the integral, and the integral is slowly going to increase, and it's going to slowly ratchet up the force until eventually it's spent so long below the line that the integral component has gotten so large that the force generated by the integral component now outlasts or outweighs the force of gravity, and it gets to 6. This is likewise going to oscillate a little bit, and the idea behind a PID controller is that you just mess with the values until eventually you get, ideally, a critically damped system where it just kind of nicely slides into place. Now that you know all of the advanced mathematical concepts behind a helicopter, it's time to go put them to use. You're going to choose a couple of variables that you want to stabilize. When I make mine, I either choose the angle of the helicopter, so pitch, roll, as well as angular velocities or normal velocities. So either its speed or the speed at which it's rotating. I like to do that for yaw since it just makes it simpler to control. For an angle PID, the proportional component is going to be the angle, the derivative component is going to be the angular velocity, and the integral component is going to be the sum of all of the various angles. For an angular velocity component, the proportional aspect is going to be the angular velocity, the derivative is going to be the angular acceleration, and the integral is going to be its angle rotation from its origin, which is just going to be the sum of all of the angular velocities times 1 tick. Once you do that, you're also going to want to use one of these advanced Ender pocket computers, because those are going to allow you to connect to the computers in your helicopter from a simple handheld device. You want to have it in your offhand because that lets you activate it like this, where you can still look around, you can still see stuff, whereas if you were to hold it or look at a normal computer, you get this screen, and you can't really do much with this screen. Then you use an advanced Ender modem on your helicopter's blade computer to transmit data from the pocket computer to the main rotor blade and from the tail rotor blade to the main rotor blade and back and forth and all that. And from there, it's pretty much personal preference. How you build your helicopter is up to you. You generally want to keep the center of mass approximately lined up with the main rotor blade, just because it makes it easier to stabilize. and how you want to control your helicopter, whether you want to control the angle it's pointing, whether you want to control the speed that it's moving at, or both, like I did, or some other method. It's really up to you. This is intentionally a sandbox game where you can do whatever you want, so have fun with it. If you're planning on using angular velocity, I would recommend you go look up the Wikipedia article on angular velocity if you don't know it already. It does follow that format where it gives it to you as a vector that follows the right-hand rule for the rotation of the helicopter. And it's actually very simple, because if you want the angular rotation around a specific axis, all you're going to have to do is project that angular acceleration vector onto the axis. Makes it pretty simple if you want to find the angular acceleration of the roll, for example. But the math is up to you. You're going to probably have to be fairly good at coding to make a helicopter this realistic, and just make it the way you want it. And just to finish off, I'll show you what I do. I have a pocket controller that has two modes. The main one stabilizes the angle of the pitch and the roll, as well as the angular velocity of the yaw and the velocity of the up and down movement, and a mode that stabilizes the velocity in all directions so that you can hover and land more easily. It can be real nice for taking off quickly and then coming back and just landing the helicopter. Real nice and simple. But you can do whatever you want. I hope this tutorial was helpful and showed you just some of the basics of the concepts behind, the physics and the engineering and the coding behind these. I know it obviously wasn't in depth. You're going to have to figure out most of the computer craft on your own and how to code properly in Lua, but hopefully it just gives you a basic overview and gets you started on a project if you want to do something like this. I will warn you, it does take a while to do it from scratch. So good luck, and thanks for watching. If you liked, please leave a like, and I'd be happy to have you as a new subscriber. Thank you.